Recording's rolling. It is Monday, September 29th. Okay, so I'm going to do this voting activity with you guys. So I'll talk about that here in a minute. I want to mostly take day to go over puzzles. Now, actually, this is a set of puzzles I've been doing with my AP students. So I want to show you guys what we've been doing just to check off some boxes and make sure cover all these topics. But really, when we get to it, want to look at you guys' chapter puzzles. So right out of the textbook, we'll just solve as many of these as we can do today after I show you guys all the stuff. Okay. And then later this week, I have some labs and activities lined up. So don't worry about FRQ, that's just AP. Right, so these puzzles that we're going to work on today, just whatever we've done in class in the next few days is all I'm going to be picking up from you guys. So as long as you're following along, just showing your work, those are going to be due on Friday. And then there's going to be a quiz on Friday on all those forces, Newton's laws, all this kind of stuff. Okay. All right, so that's the agenda. So let's look at Teacher of the Year ballot. So every year, teachers get this Teacher of the Year ballot. There's also Employer of the Year, but we're just going to focus on Teacher of the Year. All right, so we're down to these four here. We've got Miss Barnhill, Mr. Owens, Miss Wayne, and Miss Berman. All right, so I've never had these teachers, but I bet a lot of you guys have. So I'll go to all my classes and I'll ask them what they would vote for, and then I'll check one of these boxes by the end of the day. Okay, so we got Miss Barnhill. We got Mr. Owens, Miss Wayne, and Miss Furman. Okay. Now, there are different voting systems, and depending on what the voting system is, you can also get different outcomes, and so some systems might be more fair than other systems, sort of thing. Right? So today I want to take you guys through a process that's called ranked choice, where you rank your choices, like who do I like best, and who's my second favorite, and so on. Right? And there's a way to process ranked choice called instant runoff. Right? There are other ways to process ranked choice, also like a Condorcet method and so on. But normally, if people mention one of these, they go hand in hand with the other. Right? And that's in contrast to a different method that's called first past the post. Okay. And I think a good way of explaining these different types of systems is to just go ahead and simulate what an election would look like and show you guys, well, in one system, you would get one outcome, in a different system, you might get a different outcome. All right, so with these four right here, what I want you guys to do just individually, this could be in your mind or on a piece of paper, is rank in your mind who's your favorite and second favorite and so on. So I'll give you guys for example. So if this was your ballot, right, you go to the ballot box, you see these four. Okay? Suppose, for example, you really like Miss Berman the most. So now, if this were what's called a first past the post system, which is actually what most states in the United States use, including Florida, then you just check one box or bubble one bubble, and then that's it. That's all you get, and then you just walk out of out of the ballot box. Right? Okay. But if you get to rank your choices, then there's a little more to it. You say, okay, well maybe I like Miss Berman the most. Okay. But maybe Owens is a close second, and maybe that's all you know. Maybe that's I've had those two teachers, and maybe I don't really know the others, so I'm just going to rank those two, right? Right? Or if you want to, you could rank as far as you want. Maybe you really like Miss Barnhill. I'm just making up for examples, right? I've been changing my examples all day today, right? So you could rank as few or as many as you want. In fact, if you just want to rank one and nothing else, I guess you could, right? Something like that. Right? And then what happens behind the scenes? So you turn this ballot, and this all your rankings on it. So behind the scenes a machine will tabulate all the number one votes. And if there is a majority, then, well, that would be the winner. Right? But if there's not a majority, then there's a little more to the process, and it takes the majority. Right? See, here, think about this. Suppose Ms. Berman was your favorite. Right? And if you were in a first past the post system, which again is what we actually use in Florida, then you wouldn't just vote for your favorite because they were your favorite. You would also say, well, how is everybody else voting? Because what if you were the only one who was going to vote for Miss Berman? Well, in that case, if you voted for Miss Berman, you'd be like throwing your vote away. Like it would be a wasted vote, right? And so it's not just preferred voting; it's also strategic voting, right? But if you get to rank your choices, then if the machinery behind the system says, okay, well, you were the only one who voted for Miss Berman, then what it'll do is it will default to your second choice and so on. And it'll keep defaulting until there's a true majority. Okay? So you don't have to worry about like spoiler fact or strategic voting or anything like that with the ranked choice system, which is actually what we're going to do. So I'm going to scratch out my examples here. Okay, so remember this is just examples, right? Like how you can fill out such out. Right? Is there any questions so far about anything? Okay, and so I'm just gonna go get a show of hands because we're gonna do sort of a fast version of this. So show of hands as to uh, who is your number one. Right. So does everybody have in mind who their number one preference is? Number one preference. Right. Again, don't worry if you're the only person voting for them in the system we're going to use with this ranked choice. There's no such thing as wasting your vote. Right. And you guys will see why as this plays out. Right. Right. So who is going to vote for Miss Barnhill as their first choice? Who likes Miss Barnhill the most on this list? Got one, two. Okay, so pick a couple of votes here. Okay. Who likes Mr. Owens as their number one? Number one, Mr. Owens. One, two, okay. Three. Is that three?
But if I want to vote Mr.
Huh?
Popping, Sam.
Huh? Oh, we just got these four right here is what we're doing. Okay. Right. Right. How about Miss Wayne? Miss Wayne, you got one, two, three, four, five. Okay, so five for Miss Wayne. And Miss Berman. Like Miss Berman, number one. Right. Got two. Got two. Right. All right. Okay. So right, there's like the first round in a ranked choice system. Okay. And again, to contrast systems, because if this were a first past the post method, then who would win the race? Yeah, Miss Wayne would be the winner because she has the most votes. Right. But what about a little bit different question here? Who has the majority in this case? No. Nobody. Nobody has the majority. What Miss Wayne has is a plurality. Right? She has the most votes, but she doesn't actually have over 50%. Right? Like what about like if you did not vote for Miss Wayne, if you want to vote for one of these other three, okay? What if all these votes sort of congregate behind like Miss Berman, for example, or something, just to pick up something, right? I mean, it's possible that one of these three might get more votes than Miss Wayne by the end, which actually is how it was worked out in my first period class. It worked out pretty much like that. So what I'll do here is I'm going to eliminate the fewest number of, or sorry, the lowest first place, right, which would be in this case Miss Barnhill and also Miss Berman. Okay, and we're just going to have a straight runoff between Mr. Owens and Miss Wayne. Right. Okay, so now, from a voter point of view, you don't actually have to go back to the ballot box. This is all taken care of on one ballot by your ranking system. This is more like behind the scenes. What behind the scenes the ranking system will do is to say, okay, well, these can't be the winners. So who was their second place? And then it would default the votes on down the line. Right? Right. So we'll just show of hands and what's going on behind the scenes. Right. So now between these two, right, scratch out these, the 3 and the 5 gone. Right. Right. Just between Mr. Owens and Miss Wayne. Who prefers Mr. Owens? Mr. Owens. Who goes for Mr. Owens? 1, 2, 3, 3, 4. Looks like 4. Okay. Who's voting for Miss Wayne? Miss Wayne got 1, 2, 3, 4, 5, 6, 7. 7. Aha. Okay. So yeah, see how it's the same total as before? Like there were 11 to start with, and there's 11 now. Okay. But how the votes distributed right now, Miss Wayne has a true majority. Right, true majority. So she'd be the winner, and I guess either system in this case. If you went with first past the post, she would have won anyway. But even with this full runoff method, she wins. Okay. Now, show you guys how my first period class worked out because this was a little more interesting. First class, Mr. Owens actually would have won the first past the post method. Okay, but then after we went through another iteration, actually, this one came out on top there too. Okay. All right. So yeah, I will mark you guys period 7. Right. I'll look to see how all my classes were recommending today, and I'll check one of those boxes and have a good one. All right. So yeah, hopefully you guys learned a little bit about science of voting systems right there. All right. Let's look at maybe something a little weird today is just show you guys the notes from my earlier class, my AP class, and then we'll get to you guys' puzzles as soon as we can. All right. So I did have to tell my AP students about center mass because there was a center mass question that came up in the AP materials, right? And then so I know if I don't teach this to you guys now, then a few weeks from now I'll be confused and forget who I taught what. So I'm just going to make sure that I cover the bases for everybody. Right? So center mass is like where's sort of the central location of it could be a giant mass or a whole mass system. Right? Like what if there were these two masses right here? And suppose they were like stuck on a stick. Could you imagine it was like a dowel that's stuck between two, like speared them? Right? Maybe that dowel has very little mass itself, but these are like two giant masses, something like that. And I want to know like where's sort of the center? Like where could I balance it on my finger? Ooh, do you think I could balance it on my finger? Or hang it from a string? What if I hang it from a string at the center mass point? Could do that, right? Also this. What if I take this whole system, which is like stuck, there's sticks stuck there, and I throw it through the air, it starts spinning. That's what point it spins about, the center mass point. And it looks like this mass A is larger than this mass B. So you guys see how the center mass is
closer to the larger mass. We think that makes sense too, right? So how do you find that mathematically? Well, here's a general case, and then down here it's as applies to these two masses, right? So the general case is, now, see if you guys can read this. Guys, what does this mean right here? Sigma is the sum of, like I'm adding up. Okay, what am I adding up here? Mass times location, and the sub I is just me, like 1, 2, 3, 4, 5. Like I'm adding up. Right. In this case, I got two options, right? 2 points. Okay. So mass times location, right? Add all those up. There'd be some number of kilogram meters, right? Then divide by the sum of the masses in kilograms, and it gives do you guys see it's what like a weighted average, right? And it'll tell you the average location. Now this is only along the x-axis, right? Along the x-axis, right? So, for example, if I had these two masses and I want to know what's the center mass between these two, I go the first mass times this location plus the second mass times this location, again on the x-axis, divided by the sum of masses, it'll give me the average location, which is always going to be closer to the larger mass. Right? You guys that? Okay. So, how did this work out earlier today? Okay. So here's a two-dimensional example. You guys see an x, y plane? You guys see it? And I labeled three masses on here. Right, so I came up with some wacky masses. We got 72 kilograms, 11 kilograms, and 28 kilograms. You see that? Okay. So what if these were all like stuck in a foam board? What if I glued all these masses to a foam board? And the foam board was very small mass itself. Okay. I wanted to balance it on my finger. Like where would it sort of balance? Okay. So I have my average x location here. Okay, if I zoom in here, I got the first mass times this location. Do you guys see how along the x-axis this is at the coordinate -2? Right. And then this little 11 kilogram guy is at the coordinate, well, the x coordinate 1, and this 28 kilogram guy is at the coordinate 3. That's exactly what this does right here. So 72 times -2, 11 times 1, 28 times 3. Okay, so they're all kilograms times meters. Okay, I add them all up, or plus, and then divide by the sum of the masses. That gives me the average location and along the x-axis, which would be -0.44 meters. Right, so that'd be sort of like back here. I guess I marked it with a little tiny arrow. Maybe 0.44. Okay. You do the same thing in the y direction. You see in the y direction, this 28 kilogram guy is sitting on the x-axis. That'd be location 0 in terms of the y-axis. Right. And then this big old mass is sitting at the 1 unit, and this little tiny 11 kilograms is up here at 4, like 4 meters up. Okay. So same thing. So I got 72 times 1, got 11 times 4, got 28 times 0, divided by the sum of masses. The average y location is like a meter up, 1.05 meters. Okay. So it's like right here. So that coordinate, -0.44, 1.05, that right there, bam, is the center mass of this whole two-dimensional system. Okay. So you guys can do that, like a weighted average. Okay. All right, so that's one example I did earlier. Okay. We're looking at, do you guys remember doing that lab where you took all these spring scales, right, and you made like a whole vertical chain? And the top spring scale had to hold all the weight beneath it. But by the time you got to the bottom spring scale, it only had all the one weight beneath it, which was not as much. Right? Well, you can turn this into sometimes what I call the train game. So you could turn it horizontal, and what if there was a train that was pulling all these box cars behind it, all these box cars, and I want to know what's the tension in these links. You guys see how this is basically the same thing? Do I just turn this vertical? Hey, look, that looks like a chain gang. Turn it horizontal. Hey, it's a train. Yeah, same thing, right? Now, here, side question. See if you guys can figure this out. Critical thinking here. What if this whole train and all the boxcars were moving at constant velocity? Constant velocity. Guess what would be the tension in these links for constant velocity? 0. Yeah, there'd be no tension at all. Right? They're all just in motion. It sounds like Newton's first law of motion, doesn't it? Right? So this really only works. Like you can only solve for tensions if there's an acceleration. So here, as an example, I said, what if the acceleration is 3 meters per second squared? Yes. If I give you the masses, you guys see all these boxcars have masses in kilograms, and I give you an acceleration, and I'm asking for a force because tension is a force. Does that sound like a job for Newton's second law of motion? F equals ma. Right? Right? Okay. So in this case, this first link has to pull all the cars behind it. That's a lot of mass. So tension A, I had to have all the masses all being dragged at 3 meters per second squared. So that's a huge force. And this middle link only has to pull the 2 cars behind it. So that's like 2 masses added together, 3 meters per second squared gives kind of a medium force. And this back link, this tension C, only has to pull just 1 boxcar. So mass times acceleration, and then that'd be a relatively small force. You guess that? All right, what else I got here? There was a bounce a ball off a wall question, right? Which can involve forces. Now, this poster, I'm showing like a two-dimensional motion, like a ball bounces, boing, right, at some angle. But really, I should make a new poster that just has a simplified version of what if the ball is headed straight towards the ball and bounces straight away, boing, something like that. Okay? So the question could be, what's the force from the wall on the ball? Okay. Guys, is it true that because the ball is changing direction, but when the wall is putting force on the ball that's causing it to rebound? That's true, right? Okay. Is there also a force from the ball on the wall? You guys, which force is bigger? Which force is bigger? The force from the ball on the wall or the wall back on the ball? Huh?
Bouncing back.
For every force, there's an equal and opposite. Equal and opposite. So it's the same magnitude force, right? It doesn't matter how heavy the ball is or how fast it's moving or how fast it rebounds. None of that matters. The force between the ball and the wall is equal and opposite. Right? So one goes to the left, one goes to the right. Right? So what if I tell you the mass of the ball is 0.45 kilograms? That could be a baseball. What if I give you the throwing speed is like 9 meters per second? The rebound speed is maybe a little less, 7 meters per second. Let's say that time interval, delta t time interval of collision is like 0.05 seconds. Like boing, okay? There's enough information there. So you can also feed this through Newton's second law of motion. And eventually we'll call this an impulse question, but that won't be for several weeks. But you can force this into Newton's second law. So do you guys remember acceleration is rate change of velocity? Right? So in this case, okay, are you guys ready for a question that's been tripping up my AP students today? What is the difference between this rebound speed, I should say rebound velocity, 7 meters per second to the right, and the throwing velocity of 9 meters per second to the left? And don't say too, what's the difference between 7 to the right and 9 to the left? Looks like this. 7 minus negative 9. Is that true? So the difference would be minus, but it's a different direction. 16. You see a change in velocity, a delta V change in velocity of 16 meters per second? Because it completely reverses direction, doesn't it? Okay. So that's change in velocity. On this time interval could give you the corresponding acceleration. And the mass of the ball is 0.45 kilograms. Put it all together, you can get the force from the wall on the ball. So that's 144 newtons to the right. Okay. And to round back to before, there's also 144 Newton force from the ball on the wall pushing you to the left. Ooh, during that collision. There's the back. All right, so it'd be like an average net force. All right, what else have I got here? Okay, I think that's all the sort of newish stuff. We did also do an Atwood example. So here, I'll show you guys these notes that we might run into an Atwood today. What if I made up a couple of masses and I asked what's the acceleration system and what's the tension in this connecting string? Okay. So this also goes through Newton's second law of motion. Now, I saw this from the whole system approach, which is what I'm doing is I'm looking at these two weights and saying one's pulling clockwise, one's pulling counterclockwise, and they're in a tug of war. Okay. So tug of war, maybe I should subtract those two, right? Because if they were the same, they would zero out and wouldn't accelerate at all. Right? So that would give me the net force. And then can I combine those two masses and say that's the total mass? Net force on total mass gives me the acceleration. Now, once I have the acceleration, I can focus on either one block or the other block. And I can solve for the tension in the rope, which in this case, it's the same tension. Right? By the massless frictionless pulley right here. Okay, same tension. So it looks like in my math here, I focused on just this one. So I said this tension force up minus 490 newtons down. That's the net force. And there's also Newton's second law as it applies just to this block. So F equals ma. Here's your F, here's your m, and here's your a, which we solved from the whole system. So put it all together, you can solve for the tension force. It's the only thing you wouldn't know. And it comes out to some number. All right. And okay, and then I did one more with my students earlier today. I think I've done one of these with you guys already too. And so what if you have a joint in tension, and I give you the weight, and I want to know what are these two forces up here. Okay? So what's the tension force? Right? What if I gave you a weight of 20 newtons, and I give you these? I have to tell you the angles. So I made a 37 and 53 degree angle. Okay? And then what's tension left and tension right? So the big picture is this pair of equations right here, which is that. Guys, in the x direction, these two horizontal components, what do these two horizontal components have to sum to? 0, because it's in equilibrium, right? And then in the vertical direction, there's 3 that you're working with. You guys see these two pulling upward, and then the full weight pulling downward? That also has to sum to 0. So you have to break out some sine and some cosine. Okay? Now I picked 37 to 53 degrees because sine and cosine is like 3/5 and 4/5, right? Because right, that geometry. Right? So anyway, I put together a system of equations. Here's my two equations right here. We went through some math, like I know I've done with you guys the other day, and it came out. Okay, there's a little more to the math here. If you're my notes, it's right. So tail end, so I ran out of paper. There's a lot of couple steps right here. So it came out to 16 newtons and 12 newtons. So this was 16 newtons, this was 12 newtons for a 20 newton weight at those particular angles. All right. All right. So I'm going to check those boxes off, you guys. We didn't quite get that one. It's all right. All right. So let's look at your guys' puzzles. Your guys' puzzles are here. I know we've done some of these already. As long as you guys are doing these with me, then you guys turn these in on Friday. I'll give you guys credit and grade go through those. And then, of course, I'll get you guys your quiz by Friday, which is going to look a lot like a lot of these questions. Okay, so all these pink check marks, I think I already did with you guys. So let's do, how about number 21? Let's go down the line here. 21, as far as we can. A designer is trying to determine the type of wire used for a pendant light that will hang from the ceiling of an elevator. Ooh, okay. Now, even without reading anything else, the reason that you would have an elevator is, guys, could the elevator accelerate upwards and downwards? Yeah, and it would be going in one dimension, just either straight up or straight down. That's almost always why the physics textbook would even have that scenario. So I'm guessing it's going to have something to do with the elevator accelerating problem. The wire can withstand a force of 82 newtons before breaking. Therefore, the upward directed force on the lamp, called tension, cannot exceed 82 newtons. Okay, a little filler system right there. The lamp also experiences a 45 Newton gravitational force, which is, of course, weight in the downward direction. The maximum upward acceleration, what is the maximum possible acceleration? The lamp has mass 4.6 kilograms, which is kind of overkill to give me that detail because we could figure that out too. Okay. Here, I'll show you guys how. So let's draw this up here. You got elevator. This is number 21. 21, elevator. Got elevator right here. Okay. And there's a lamp hanging from the ceiling. So like that. We're going to draw like some kind of lamp or something, right? Whatever a lamp looks like. All shiny, probably. Okay. Okay. And what are the forces acting on this lamp? Here, I'll start from just the mass. So, switch color. Well, how about black ink? Let's go. The mass of this lamp is, they said 4.6 kilograms, right? 4.6 kilograms. Okay. And just looking at the numbers they gave, I think they're tending towards gravity field is going to be 9.8 meters per second squared. Right? I think that's how you get the weight out of that they gave us. But we'll find out for sure. But I'm pretty sure they use that number. Right. Also, you know the maximum allowable tension in this, what do you call this? A rope. A wire. Okay. Maximum possible tension in the wire. Okay. Here, let's finish off the three-body diagram. So, do you guys think this lamp has a weight that's pulling straight down? And I could call that mg. Come back to that. And also a force pulling straight up. Now, if the whole elevator is accelerating upward, then which force are you drawing bigger? The up force or the down force? Up. Yeah, the up force. It's being pulled up a lot more than it's being pulled down. So I'll call that up. Okay. And this could be like T max, like the maximum tension is allowed to go up to 82 newtons. Okay. So that's like the breaking point. So if there's some kind of upward acceleration that results in that tension, then that's as much as you're allowed to accelerate upwards. And that's what we're solving for. Okay. Now, how about this mg? Well, here's m and here's g. So can we just multiply those two together and get the weight? You guys see that? Okay. Right, so let's do 4, 6 times 9, 8. Okay. Looks like, hey, there you go. There's 45 newtons. And they also gave you the weight. But I just wanted to confirm that that's where they got it from. Yeah, there you go. So that's 45 newtons. All right. Okay. What's everybody doing here? You guys all writing stuff down? Guys all.
Right. Got paper. You guys write stuff down. Okay. So, okay. All right. So, have those forces right there. Now, let's set up. Here. If you know something about forces and you know this mass, and you want to know something about acceleration, what's this all going to feed into? What law of motion? Newton's second law of motion. Is that right? Newton's second law of motion. Right. Which goes like net force results in mass times acceleration. Right. Or you could rearrange this and get acceleration is net force over mass, which is usually how I like to think of it anyway. And actually, that's exactly what you need to solve for acceleration. Okay, so that's not, so acceleration is, well, guys, what is the net force in this case? How do you find the net force? Is it 82 up and 45 down?
37.
Yeah, so whatever, whatever 82 newtons minus 45 newtons would be like that, right? Okay. And what mass is that acting on? 4.6 kilograms. Right, that true? Just like that. Okay. So the really this is a maximum acceleration to pair with that maximum allowable tension. Okay. So this is like A max is what it is. So the maximum allowable acceleration is 82 minus 45, then divide by 4.6. Looking at 8.04 meters per second squared. Okay. So if the elevator is accelerating upward at 8 meters per second squared, then this wire is barely hanging on. But if you go up to like 8.1 meters per second squared, and forget it, that wire is going to snap. Okay. Okay. Right. Oh, that would be a ridiculous acceleration. Because, you know what? I've got my own follow-up question about this. I suppose you're standing inside this elevator at the same time. Approximately, like to the nearest whole number, how many G's do you feel? Oh, yeah. Okay.
Oh, what's that you wrote below the A?
Max. So like the maximum allowable acceleration. Okay? That's the question. Because this tension can only go up to 82 newtons. So if we plug that in, 82 newtons, this would be a maximum allowable acceleration. Okay. Okay. So is it right now sitting in this room, do you guys feel one Earth gravity, right? One Earth gravity, which is like 9.8 meters per second squared. Okay. If you're accelerating upward on top of that, almost an additional G worth, this guy feels what almost 2 Gs, right? Because if there was no acceleration, if the elevator was accelerating at 0, this guy would feel one Earth gravity, right? Just like sitting at rest, right? Or constant velocity, right? But this is almost one full G on top of that. So this guy feels almost twice as heavy as he normally does. Yeah, yeah. I mean, same thing is true for the lamp. We could have looked at that, right? The lamp normally weighs 45 newtons, and this tension is going up to almost twice as much. Yeah, it's all there. It's all there. So 21. Here, last thing with 21 is I do have a poster that's really similar to what we just did, well, sort of. Okay? Here's an upward accelerating elevator, just like that. Now this is geared towards a little different question, saying what would the normal force reading be on a scale, or you could have said that the tension in the wire, right, equivalent, right, in terms of the acceleration. But you could also rearrange this and solve for acceleration, right? And then, yeah, that's what we did. So very, very similar premise right there. So got that. All right, let's go number 22. 22. A designer is trying to determine the type of wire to use for a pendant light that will hang from the ceiling of an elevator. Okay, this is like a really similar scenario, doesn't it? The wire can withstand a force of 70 newtons without breaking, therefore the upward directed force of the lamp can exceed 70 newtons. Wait a minute. Is that the same question with different numbers?
Maybe.
Yeah, it looks like the same. Huh. Okay. Yeah, let's get past that because yeah, it was basically the same question, just different numbers. All right.
Does that mean we don't have to do it?
Yeah, don't worry about that one. Right. Okay, so we did 21. We're just gonna skip 22. Right, number 24. A trapeze is a short horizontal bar held up by 2 vertical ropes on either side. An acrobat with a mass of 60 kilograms provides
and 588 Newton downward force on the bar. Each of the two trapeze ropes provides an upward force of 349 newtons. What's the upward acceleration of the acrobat? Ooh, let's draw this out. So 24. And so maybe here's their trapeze, something like that. There's a couple of vertical, they call it ropes. Yeah, vertical ropes. Pull it up, something like that. And then maybe you got this this guy right here who's pulling down with some weight. It's basically like that, right? Like that. That's what's going on. Okay. And they told you this guy's mass right here is 60 kilograms. So you know that. They told you that 60 times 9.8, that's probably where they got this 588 Newton weight. I think that would make sense. Let me double check. What's 60 times 9.8? Yeah, that's exactly where they got that from. 60 times 9.8. Okay. If they did not give that to you, I'm sure you could have figured that out. And then they're saying each of these trapeze ropes call a tension of 349 newtons. Now that's for both, well, each of them, right? Each of them is 349 newtons. Okay. So that's what's going on right there. Right, so I see two upward forces and I see one downward force. Is that okay? Can you guys find the net force? How would you find the net force? Yeah. So add these two up, subtract this one down. It'd be like 349 newtons plus 349 newtons minus 588 newtons. That'd be like a net force, wouldn't it? All right, so let's go 349 plus 349 minus 588. Okay. So put it all together, the net force is 110 newtons. Okay. Now that's not the final answer yet, but that is an important middle step. So you guys see the net force on the sky is that much? Okay. The question though is what's the acceleration? So guys, if you know the force and you know the mass, how do you find acceleration? Yeah, force on mass. Yeah, net force on mass. It's just Newton's second law of motion all over again. Okay. So yeah, first 20 minutes of class I did a bunch of questions that involved Newton's second law. The last question involved with the elevator. Okay. There's Newton's second law right there. Okay. And now we got Newton's second law again. So it looks like Newton's second law of motion is showing up all over the place. Okay. So we'll feed everything into this. So here's your net force. Here's your mass. What's right there? So the acceleration is about 110 Newton net force acting on 60 kilograms mass. So 110 over 60. All right, so that's 1.83 meters per second squared because it's an acceleration. That's it. That's the answer. All right, you guys get that? So while you're writing that down, digesting that, go over that one again. Okay. So they gave you the mass of the sky and the weight of the sky. They told you he's on a trapeze pulling up with two ropes, and they told you the tension in each rope. Okay. And then what's the acceleration? Okay. So say, okay, well, if I want to know acceleration, I know it's going to feed into Newton's second law of motion at some point. Net force on mass. So I got to find the net force. Okay. Net force is two tensions up, add those together, weight down, subtract out opposite direction. Now we have the net force that feeds in right there. Net force acting on what? Oh, this guy's mass. Feeds in right there. Okay. So Newton's second law of motion, divide force by mass. That gives you acceleration. That's it. You guys good? Okay. Now, my sort of follow-up idea to this is like, what's actually going on here? So it could be one of two things. So this guy could be sort of starting from rest and he's just pulling it really hard, like pull himself up, kind of like a little mini elevator. Right. Maybe with about 1.2 G's. He probably feels about 20% heavier-ish than he normally would if he did like that. Right. More likely what's going on is, if you ever see something like this, isn't normally like swing, like swing like that? You guys see that? Swing? Right. Now, a few weeks from now, we're going to bring in circular motion. So what happens when you're on a curved path? Okay. And the force that pulls you up, in this case, like that, well, the difference between the tensions up and his weight down, which we found right here, this net force, would be called centripetal force in that case. And it depends how fast he's moving, like in a linear sense, if you point a radar gun at him, and also what's this radius of curvature. Okay, so it's more likely what would lead to a scenario like this. Yeah, if you're like swinging on a swing, how about that? Let's talk about swings because this is basically the same scenario, isn't it? Right? You guys ever sat on a swing? Right? Like this guy's sitting on a swing right here, like swing, 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 swing. Okay. Is if you threw down the scale and you were sitting on the scale at the same time you were swinging, would that scale read your same weight, or would it look really like you're really, really heavy? Yeah, you would look heavy. Like if you normally weigh 100 pounds, I bet the scale reads like 110 or 120 pounds. Right? Just like this guy right here. Right? He's accelerating for that reason. Right? So it's sort of some future content right there, like in the sense of like why would there be an acceleration? So look for that when we get to rotational net motion. All right, so you guys get on this trapeze guy? Good. So check. All right, number 25. Ooh, I got this one highlighted because I think it looked like one of your labs from last week. A horse is dragging a crate behind it. Oh, sounds like friction. The horse applies a 60 Newton force to accelerate the crate to the right. The crate experiences a 10 Newton force in the opposite direction due to friction. The crate's acceleration is 0.67 meters per second squared. What's the crate's mass? Oh, yeah, that sounds like the job, again, for Newton's second law of motion. So we got a Newton's second law scenario again. Right? But here, just to be more complete about this, let's look at a full three body diagram. Like here's your crate. Here's like a horse. Right, he's like pulling this crate. Okay. And then, okay, so what are all the forces on this crate? This crate has some mass. Okay, no switchy color. Okay. It's got some weight, mg. Okay. Now we don't actually know the mass of the crate, right? Because if the force is pulling horizontally, then wouldn't this normal force just be equivalent in magnitude to the weight because there's nothing else vertical going on? Right? That's simplified a little bit, right? So this force is pulling forward. I'll call this, how about a tension force? Okay, the tension of these ropes right here. Did they tell us that force? Yeah, they said 60 newtons. 60 newtons. Right? And they said there's a back force, a friction force. This is F sub FR friction force of 10 newtons. Right. So there you go. That's what we have. Oh, there's one more detail. Acceleration equals 0.67 meters per second squared. Okay, so those also given point for. Okay, so we're supposed to find the mass of the crate. Okay, but I got one more follow-up question. I want to know, also find the coefficient of kinetic friction because there's enough information on the board here. We'll be able to also find that. So we're going to find both of these things. All right, you guys ready to chase down both these numbers? Okay, so let's start with the mass of the crate. Right.
This is number 25.
Yeah, 25. 25 right here on the horse. Okay, so guys, how can you find the mass of the crate? If you know some forces going on and you know the resulting acceleration, what formula can I plug this into? What equals what? F equals ma? F equals ma? Okay. And when I say F equals ma, what force are we talking about here? Net force. Okay. Right. Which is really like, if there is a single force, then that would just be also the net force. But if there's lots of forces going on, you have to add them all together as if they were acting as a net force. Okay. Now the two verticals just cancel anyway, so I can just ignore those. For now, I can. Okay. But what about these two horizontals? One pulls to the right with 60, one pulls to the left with 10. Okay. So is this right here? 60 newtons to the right minus 10 newtons to the left. That would be the net force, wouldn't it? Of 50. You guys see the net force is 50 newtons? Great. 60 to the right, 10 to the left. All right. Make sure you guys are okay out here. All right, ready to solve these? Ready to solve these? All right. Here we go. Yeah. All right, and that's gonna act on, well, some mass we don't know, okay, but we do know the acceleration. That's this right here. They gave us the acceleration. Right? Okay. So see, I got this net force, got this resulting acceleration. Ah, can you guys find the mass now?
What is mu representing them?
Oh, this is the coefficient of friction. Right. So we're not quite there yet, but in a few steps we'll be able to also find that. Okay. Right. So coefficient of friction is what's the ratio of friction force to normal force? It has something to do with like the crate and the dirt and something like that. Right. But for now, we're just going to find the mass. So 50 divided by 0.67. I'm looking at 74.6 kilograms. Right. So that's the mass of the crate. Okay. You guys good with the mass of the crate? Next. Okay, because we have enough forces, we can find this out. They gave us the resulting acceleration. There's got to be only one mass that acts on. Okay, that goes in there. Okay. Now, what about this follow-up question? Okay. You guys remember coefficient of friction? Here, coefficient of friction is the ratio of friction force compared to normal force. You guys remember that? You guys did a whole lab on that about a week ago. Yes? Okay, and I know what the friction force is. Because they gave that to us. They said, oh, that's 10 newtons. So that one's easy. And now the normal force, well, yes, what's this normal force? What is that?
The thing that the weight or
It is equal in magnitude to the weight. Yeah. Because this crate is pressing down the ground with its weight, and the ground's pressing up, holding up with equal number of newtons. So we need to chase down the weight. Okay. So can you guys do 74.6 kilograms times 9.8 meters per second squared? Right, this reason 9.8 for the book, meters per second squared. Let's see, what's the weight of this thing? 74.6 times 9.8. I'm looking at 731 newtons. Okay. So this crate weighs 731 newtons. That's how much it's pressing down the ground. Therefore, is the ground holding it up with 731 newtons? It's gotta be. So now we can find the coefficient of kinetic friction. So I have a 10 Newton friction force acting on 731 newtons normal force. Is that? And so what's 10 over 731? Okay. That is, now that's really, really small. You see, it's like about 1%. It's between 1 and 2%. You see that? Between 1 and 2%. Right? Which really makes me think that this crate's probably on wheels. Right? You guys think? Right. Yeah, it's probably on low wheels, right? Because if it was actually like scraping against the dirt, this would be like much, much higher. Right? It'd be probably at least 10 times higher. Okay. Yeah. Yes, it's probably on low wheels right there. You guys good? For the horse in the crate. So number 25. Check it out. Number 30. Hey, use my.
Can you go back
Oh,
one second?
yeah.
I sort of missed that one.
Alright, so here, let's do a recap here. Right, so they told you two forces, the tangent force forward, the friction force backward, and they also gave the resulting acceleration. Okay? Now, from that you can get the mass. You guys go through Newton's second law of motion and say, well, the net force is the difference between those forces, they're opposite directions. You go on acceleration, boom, boom, and then you can solve for the mass by dividing. Okay? That's all they ask for. Okay. Now I'm going the extra step saying, we can actually find the coefficient of friction also, which is ratio of friction force to normal force. Now the friction force they directly gave you, so that's not hard. Okay. Now what's the normal force though? Well, the normal force would be equivalent to the weight, and the weight would be mass times gravity. So if you take that and then plug that in basically there, and then get the coefficient of friction. All right, so you guys good?
Sure.
Yeah. All right. Number 30. We get to use mathematics. How exciting. A helicopter is used to rescue a skier trapped by an avalanche on the side of a mountain. A cable attached to the helicopter is lowered and attached to the skier. The downward force of the skier due to gravity is 700 newtons. The sky weighs 700 newtons. The skier is lifted at constant velocity. What is the magnitude of the force exerted by the cable on the skier? Guys, the key to this whole thing is constant velocity. You guys see that constant velocity right there? Bam. Okay. So, number 30. Okay. Let's draw this out. Okay, so we got helicopter. Something like that. Okay. We're lowering down this rope. And here's the skier right here. Okay, so there's the scenario. Let's do a free body diagram. So This guy has a weight of 700 newtons. But also pulling up on this guy is a tension force. Right? So weight down, tension force up. Isn't that true? Right? And guys, since he's being pulled up at constant velocity, what is the acceleration equal to?
0.
0 meters per second squared. 0. And if that's true, do F equals ma. If the acceleration is 0, what is the net force?
12. What's that?
0. 0 newtons. Right? Because if there's no acceleration, there's no net force. Right? But there are two individual forces. So do you guys think the tension force up minus the weight down would give you the net force? Which of course is 0. Is that true? Right. And if the tension, so we're solving for tension, right? So tension force minus 700 newtons goes to 0 newtons. So what's the tension force?
700.
700 newtons. That's all. Right? It's kind of overkill, maybe. Right? Some of you guys may have seen that like a whole minute ago. So, oh, okay, well, it's got to be 700 up to balance to 700 down. That's the only thing that would result in constant velocity. Yeah, that's it. Notice they didn't even say what velocity it is. Is he being pulled up at 10 meters per second or 20 meters per second or 30 meters per second? It doesn't matter as long as it's constant. So what's that? Okay, you guys check that?
41.
So check that one off.
No.
Okay. I'd like to do some of these other ones, but yeah, we are short on time, so we'll save some of these for another day. I think we've made pretty good progress today. I showed you guys a bunch of examples, and then we solved a bunch of these from the book. Yeah. Clicking along.
Oh, I'm ready. No.